Hello everyone, and welcome to the first lecture of the Web Security course. In this lecture, we will start by exploring the basics of how the web works, what its main components are, how the HTTP protocol functions, what secure HTTP or HTTPS is, and we will take a closer look at the HTTP cookies mechanism, which is used to implement web sessions. But first, let's zoom out and take a very basic look at how the World Wide Web works. What we have here is a client, a web browser, and over here is a server that hosts a website or web application. Usually we have a user, a person, who uses a web browser on their device to access a remote website and use the functionality it provides, whether it is a social network, an online banking site, or something else. The communication between the browser and the server happens via the HTTP protocol. This is a request-response protocol, meaning that the browser sends an HTTP request and receives an HTTP response in return. A web resource on the internet are identified by an address, more formally a Uniform Resource Locator or URL. This identifier consists of several parts. It starts with scheme, which is like a protocol, and usually we will only see here HTTP or HTTPS. Hostname, which is basically the domain name of the server hosting the website. The TCP port on which the service is running. If it is the default port, then we don't need to include it in the URL. Then comes path, where the resource is located on the server, and query string, which typically contains key value pairs separated by ampersands. So you can think of the path and query string as parameters that identify the requested resource on the server. Now, the last part of a URL is the fragment, which actually is a hint to the browser about which part of the response it should scroll down to. Note that this part is actually not sent to the server, while the path and query are. So when we enter a URL into the browser's address bar, a DNS request is made to resolve this domain name to an IP address. Then the browser connects to that IP address, sends an HTTP request with these parameters, receives a response, and renders it for the user. The user can then interact with the website, click on links, submit forms, and the browser will send the corresponding HTTP requests. Pretty simple, right? Now, where can we have a security issue in this process? Well, the main issue here is that in order for a web application running here to produce a response, it has to process potentially malicious data that is received in this HTTP request. So if the application or server cannot securely process these requests, then this could be exploited to compromise the website and data that it protects. So one of the main goals in this course is to learn how to identify and prevent the most common vulnerabilities in web applications, and therefore we will focus quite a lot on how to correctly handle potentially malicious user input. Since HTTP is pretty much the only way to interact with a web server, it becomes the main attack vector that an attacker can use. Therefore, it is super important that we understand how HTTP actually works. Let's look at an example HTTP request and response. The great thing about HTTP is that it is a human-readable text protocol, so we can actually read and inspect it. So here is an example of an HTTP GET request. There are several data fields that we can identify. The first is the HTTP method that is used for the request. In this case, it is GET, but it could also be POST or other less common HTTP methods. In practice, we will mostly deal with GET and POST requests only. Next comes the path that we want to request on the server. So this here is the path and query string from the URL. The last field specifies the HTTP version. We will focus on version 1.1 in this course. Newer versions also exist, but they are not significantly different from 1.1, at least not in the terms of the security aspects that we will cover. What follows next is the request headers. These are key value pairs with extra information about the request. Some headers are standardized, but servers and clients can also define custom headers. We will look at some of the headers in the following slides. After the headers, an empty line is sent to the server. This way, the client signals to the server that the client is done sending headers and the server can now start working on producing the response. Here is an example HTTP response returned by the server. The response starts with the HTTP version matching the one in the request, and then comes the status code and status phrase. These tell the client if the request was successful. 200 status codes signal that the request was completed successfully. 300 codes are redirection responses. 400 codes signal that there was some problem in the client's request, and 500 that there was some error on the server side while processing the client's request. Anyhow, after the status line, the server returns response headers just like the client sent request headers. Now, to signal that the server has completed sending headers, the server sends an empty line here. After the empty line, the server sends the response body that contains some data. Now, the data here could be some HTML response, as you see here, but it could also be an image or contents of a file for download. Now, the question we have to answer here is, how does the client know when the response ends? Well, the answer is that the amount of data is specified in the content length header here. Without it, the client would not know where the response body ends. Very good. So as you can see, an HTTP GET request allows the client to request data from the server and receive a response. But what if the client wants to send or upload data? While some data can be included here in the URL or headers, there are size limits, usually just a few kilobytes. So for larger payloads, we can use the HTTP POST request. Here is an example POST request. It looks similar to a GET, except that the method is POST, and after the headers, the client can send some data of arbitrary length, which is specified here in the content length header. So the difference between the GET and POST requests is that POST requests can have a request body, while GET requests have an empty request body. From a security perspective, the rule is that sensitive data must be sent in a POST request body. For example, passwords should never be sent here in GET parameters, but rather in the POST body, as you see here. The reason is that data that is sent in the POST request body is not visible in the URL and is not logged in the server logs that are visible to server administrators. Therefore, this reduces the risk that this sensitive information could be seen in the server logs or browser history. Anyhow, in essence, this is how the HTTP protocol looks and works. Now, let's briefly cover a few important HTTP request and response headers. For request headers, the host header is included in all HTTP requests. It tells server which hostname the client wants to access. This is the hostname from the URL. A single server can host multiple websites, so this header is essential. User agent identifies the browser and OS version. The term user agent is used in technical standards when referring to browsers and other HTTP clients. All browsers send this header, and it does have some privacy implications, which we will cover later. The refer header, yes, it is misspelled, contains the URL of the web page where the request originated. So if someone clicks a link to our website from another website, we will see that website's URL in this header. This is useful for analytics, but again, it raises privacy concerns, especially if sensitive info is in the URL. Websites can specify a referrer policy to prevent browsers from sending this header, but this has to be configured by website developers. For response headers, the server header may contain server software version. Depending on how the server is configured, this header may even include the specific version of PHP that the server is running. It is usually a good idea to disable this for security reasons. Content type tells the browser how to interpret the data that is in the response body. For example, whether it is an HTML code, an image, or some file that should be downloaded. As you will see later, setting this value incorrectly may lead to security issues. Location is a header that specifies a URL to which the browser should be redirected. So as soon as the browser sees the location header, it will take the URL specified in the header and it will try to load that URL. So this is one way how a website can implement a redirect to its own website or another website. Alright, these were some headers that are useful to discuss at this point, but we will discuss more headers as we go into various other topics covered in this course. Let's now recap the main building blocks of a modern web page. HTML, or Hypertext Markup Language, is a core building block of a web page. Essentially, it is just text with tags that browser interpret. CSS, or Cascading Style Sheets, is a language that is used to control the visual style of HTML elements on a web page. CSS can be embedded in HTML file, as you see here, or stored in separate files. And while CSS seems simple, the language actually supports quite powerful features that can be used to implement animations, layout tricks, and even games written in pure HTML and CSS. Then it is important to mention the DOM, or Document Object Model, which is a tree-like data structure that represents the page where each element is a node with tags, attributes, and children. The DOM provides programmatic access to the web page. For instance, CSS works by applying style information for certain elements of the DOM. So when a browser loads a page, it parses the HTML into the DOM tree, and then the rendering engine uses the DOM to draw the page based on that structure. We will refer to the DOM quite a lot in this course. And then, of course, we have JavaScript, which requires to be covered on a separate slide. JavaScript is the programming language of the web. It runs inside our browsers and can be used by a web page to provide an interactive web experience. For instance, this code will render a button, which when clicked will execute this JavaScript code and display a random number. JavaScript is a general-purpose programming language pretty much like any other language. The main difference is that for security reasons, browsers perform sandboxed JavaScript code execution, meaning that JavaScript cannot access files on our computer or interfere with other websites. We will discuss in the next lecture how this sandboxing policy works. Nevertheless, JavaScript has very powerful capabilities. First and foremost, it can be used to navigate and dynamically modify the DOM, which essentially means that it can modify any part of the web page. For example, this JavaScript code modifies the content and color of this heading element. In a similar manner, it is possible to add new elements and remove existing ones, and once the DOM is modified, the browser will re-render the page, making the changes visible instantly. JavaScript can also handle events. For instance, here it was invoked on the event of a button click. As you will see during this course, there is quite a rich set of events that can be handled by JavaScript. Then JavaScript can make network requests. Usually, this is used to fetch more data from the server. And JavaScript can be used to call browser APIs, for instance, to access the camera and microphone. Calling APIs is the main way in which sandbox JavaScript can interact with the outside world. The functionality of the web nowadays is extended mainly by browsers introducing new APIs that a website can access via JavaScript. So these were some of the capabilities to mention, and during this course we will look at them in more detail. Today, most modern web pages require JavaScript. Perhaps 10 years ago it was possible to browse the web without JavaScript enabled, but that is not the case anymore. So-called single-page applications are gaining popularity. Here, the idea is that a web page is loaded only once, and all additional content is loaded from the server by JavaScript without reloading the page, and therefore providing a smoother user experience. Now, all this powerful functionality of JavaScript is very nice, but the problem is that the JavaScript interpreter or compiler becomes one of the most complex and bloated components of our browsers, which means that it is a very popular attack target, as any vulnerability there may lead to arbitrary code execution and compromise of the user's machine. We will not look into this issue in this course. We will just assume that browsers are secure in this respect. Let's take a quick look at the most popular browsers and how they impact web security. So what browsers do we have? We have Google Chrome, which is the market leader, Apple Safari used on Apple devices, Microsoft Edge available on Windows operating systems, Mozilla Firefox cross-platform open source browser, Samsung Internet, which is the default browser on Samsung mobile devices, and Opera, which has very small market share. There are more browsers out there, but we will not consider those with less than 1% of market share. And while it may seem that there are quite a few different browsers, the fact is that there are only 3 major browser engines in use. These are Blink, developed by Google's Chromium project, Gecko, used by Firefox and developed by Mozilla Foundation, and WebKit, used by Safari and developed by Apple. A browser engine is the most important part of any browser, as it contains all the complexity needed to render web pages. Today, the browser engine from the Chromium project is used by Google Chrome, Microsoft Edge, Samsung Internet, Opera, and many other browsers. So internally, all these browsers are very similar. The main difference lies in the user experience around the browser engine. Chromium is also a browser in its own right, and from the user's perspective it is almost identical to Chrome, but without Google's proprietary bloatware, which is added to Chrome for better integration with Google services. Some people may like Chrome's integration with Google products, but there are privacy concerns, as signing into one Google service automatically signs you into the whole browser, making it easier for Google to track users' actions on the web. Personally, I prefer using Chromium and Firefox, since both are open source browsers that follow a transparent development process. But why are so many browsers based on Chromium? Well, the reason is that Google has invested enormous resources into the development of Chromium, and it has been designed to make it very easy to use as the foundation for new browsers. For instance, the Chromium-based Brave browser has recently gained popularity as it can include some privacy features and ships with an ad blocker enabled by default. Anyhow, today, the web has so many features that developing a standards-compliant browser engine is very expensive, and it actually takes a lot of resources from Apple and Mozilla to continue maintaining their own browser engines. Even Google's competitor Microsoft recently decided to abandon its own browser engine and switch to Chromium. This is especially challenging for Firefox, as it is essentially competing with 2 of the richest companies in the world, Apple and Google. If you look at browser market share, then this is what we see in 2025. Chrome has the majority, followed by Safari, Edge, and Firefox. And this includes both desktop and mobile browsers. On desktop, Edge, Firefox, and Opera have a slightly larger market share. However, if we group them by browser engine, Chromium-based browsers make up to 77% of the market. Since Google has overwhelming control over Chromium, there is a concern that Google alone could soon start dictating which features the web should support, and we could end up with websites that only work in Chromium-based browsers. So that's the risk of browser monoculture. So far, thanks to the market share of Safari and Firefox, this hasn't had too much of an impact yet. In general, Google has been good at improving web security. However, because of their advertising business, they have proposed some features in the past that would have seriously reduced user privacy. In this context, the US Department of Justice demanding that Google sell Chrome is actually a very positive development. Now, regarding security, there are slight differences in how each browser engine implements web standards and APIs, so it is possible that certain client-side attacks might only work against a specific browser or engine. If we talk about exploiting security vulnerabilities in the browser itself, then it is worth mentioning that Chromium and Firefox have a security feature called site isolation. The implementations differ between the two, but the general idea is to separate web pages from different sites into their own restricted operating system processes. Here is what that looks like. The security benefit is that even if evil.com manages to exploit a vulnerability in the browser and run arbitrary code, the malicious code will not be able to access the main browser process, which has access to operating system resources or other processes that may contain data of different websites. This site isolation feature makes it much harder to compromise a user's machine through browser vulnerabilities. It is important to note that the WebKit browser engine used by Safari does not offer a similar site isolation feature. And what is also unfortunate is that browsers on Apple's iOS mobile devices are forced to use the Apple's WebKit engine. This is due to Apple's App Store policies. It means that Chromium-based browsers and Firefox on iOS devices are basically Safari, just with a different skin and without the site isolation security feature. Anyhow, that's the situation with browsers. During this course, we will also explore some other security aspects where these web browsers differ. At this point, we should be able to discuss what is web security really about. In essence, there are three classes of attacks that we need to consider when studying web security. The first class is server-side attacks. These attacks target vulnerabilities in the software that runs on the server. Usually in the server-side web application code, but the target could also be a vulnerable or misconfigured web server, a database server, or any other part of the software stack. So these attacks are attacking the server, and in the worst case scenario, they can result in complete compromise of the server, which can then allow attackers to reach network resources behind the server. So these attacks should be the primary concern for website operators. Then the second class is client-side attacks. Here we are talking about attacks that exploit vulnerabilities in the client-side web application code that runs inside the user's browser. Since browsers execute web application code in the security context of a specific website, these attacks will generally be able to compromise only the user's session or account with that particular vulnerable website. Compared to server-side attacks, client-side attacks seem less impactful, but that does not mean that developers can ignore security issues in their client-side web application code. Now, the third type of attacks are web technology or browser attacks. These are also client-side attacks, but they don't exploit a particular web application. Instead, they exploit or abuse functionality in browsers' web technology in general. These attacks might abuse browser APIs, permissions, the architecture of the web, or security models built into browsers. So these attacks are attacking the user or the user's device and often include some level of social engineering. The problem with this type of attack is that it cannot be fixed just by writing more secure web application code. It requires changes to browser functionality or even to the underlying web standards. This is why web security is a much broader topic than just securing web applications by applying secure programming techniques. In this course, we will study all three classes of attacks. But let's go back to the HTTP protocol and take a look at how we can make an HTTP POST request using a browser. Making a GET request is simple. We can just type the URL in the browser's address bar or click a link. But how can we make a POST request? There are essentially two ways a browser can send a POST request: by using an HTML form or by using a JavaScript fetch call. The simplest way to make a POST request is to create and submit an HTML form. Here is an example of an HTML form with two parameters specified in hidden HTML input fields. The result of this code is just a submit button, and when we click the button, an HTTP post request is sent to the URL specified here, and the browser opens that URL and displays the result. Another method is to use JavaScript's fetch API. Here is what the code looks like. So here we have the same button as here, but when we click on it, a JavaScript function called submit is triggered, which in turn calls fetch, sending a post request to this URL. Both methods submit the same data, a username and password. However, the fetch method sends the request in the background without opening the target website in the browser. The fetch method is more powerful because it gives more control over the request and its parameters, and we will talk more about it in the next lecture. To summarize, these are the two main ways websites can make our browser send HTTP post requests. Sometimes we may need to craft custom HTTP requests. The problem with browser-made requests is that browsers do not let us fully control all the request parameters. For example, we cannot set arbitrary HTTP headers. To craft custom requests, we can use the curl command line tool. Here is an example of an HTTP post request sent to this URL. This is the data included in the request body, and here we set two request headers. We can set multiple headers by using the -h flag multiple times. So after we run this command as a one-liner in the terminal, we will see the HTTP response from the server, including the response headers. This is just one example, but curl accepts many different arguments that let us control almost every aspect of an HTTP request. There are other tools also like Postman, which has a graphical user interface, but for this course we will stick to curl because it lets us craft arbitrary requests using compact, text-based one-liners like the example you see here. The next big topic of this lecture is HTTP cookies. HTTP cookies are an extremely important mechanism that helps us to deal with the issue of how to identify HTTP requests that come from the same browser. The problem is that HTTP protocol on its own is stateless, meaning that it is difficult for a server to know whether two HTTP requests actually come from the same browser. You may ask, but why would the server need to link together requests from the same browser? Well, for instance, if we have authenticated a user using a password, we don't want the user to submit their password with every single HTTP request. So the server somehow needs to identify that HTTP requests are coming from a browser that has already been authenticated. The solution to this problem is the cookie mechanism, which is supported by all browsers. The basic idea is that cookies allow a website to store some arbitrary data in the browser, and the browser will then send this data back to the website with every subsequent HTTP request. Here's how it works. Let's say a client sends an HTTP request to access some resource on a server. The server in its HTTP response can include a set cookie header that contains a name-value pair. What the browser will do is remember this name-value pair, and it will send it back to the server in future HTTP requests in the cookie header as you see here. In this way, the server can be sure that these three requests originated from the same client or browser. So this cookie mechanism is the standard way of how today web applications implement authentication sessions. The client submits their username and password, the server issues a cookie containing a unique session ID, and then the server can track that the follow-up requests are coming from an already authenticated user. Of course, the security requirement here is that the session ID in authentication cookies must be a unique, unpredictable value, meaning that an attacker should not be able to guess or brute force it. If the session ID contains a short, non-random value, as in this example here, then the attacker could simply try accessing the server with different session ID cookie values and could hijack a session that belongs to authenticated other user. So what you should realize at this point is that it is absolutely critical to protect the session identifier, because anyone who knows the session ID can impersonate the browser session, and if the session belongs to an authenticated user, they will get access to that user's account on the website. Well, all right, how would we implement sessions in our web application? To implement sessions in PHP, we don't need to handle cookies manually. To enable automatic session handling, we just have to place the session start function at the very top of our PHP code. It will generate a cryptographically secure session ID and return it to the client using the set cookie header. If, however, the client's HTTP request already contains a session cookie, PHP will not generate a new session ID but use the session ID received from the client. So this function either resumes an existing session or starts a new one if no session cookie is found. What is neat here is that once we have a session, we can assign session variables to it. For instance, in the case of successful authentication, we can store session variables in this global session array, as we do here to store information about the user. Later, we can retrieve session data from this array. For example, here we check whether the session belongs to an already authenticated user and print the username. So it works like a server-side storage box for each user session. By default, PHP uses the PHP sysID name for session cookies. We can change the name of the session cookies and set other cookie parameters using these two functions, which must be called before the session start function. We will look at these cookie parameters in more detail, but here it is important to discuss how this session data is stored on the server side. By default, session storage in PHP is implemented by saving session files in the temp directory where the file name includes the session ID. And if we look inside the file, we will see that it contains session variables stored in a serialized form. Here it is important to recognize that not only the contents of this file may include sensitive data, but the file name itself contains the secret session ID, which must not be exposed to third parties. This creates a real security issue, especially when using a shared hosting provider. For example, on the Serve00 shared hosting platform, users do not have permission to read session data files belonging to others. But since it is possible to see the file names, that is enough to hijack a session by crafting a cookie with the corresponding session ID. This is a very common security issue on shared hosting, and in practice, it is very difficult, almost impossible, to configure a shared hosting such that one user would be completely sandboxed from attacking other users. And for this reason, preferably, shared hosting should not be used to host anything sensitive. In PHP, we can change the default session save path by using the session save path function before calling session start. In practice, we would rather store sessions in a database because file-based session storage makes it hard to implement the security features that we will discuss later in this course. For example, with this file-based mechanism, it is not easy to fetch or delete all sessions belonging to a specific user. Let's come back to cookies and talk about the methods for setting cookies. The most common way is to use the HTTP response header called setCookie. Now, cookies can also have several parameters, or more precisely, attributes that can be specified by separating them with a semicolon. We will discuss them in a second, but keep in mind that cookies can also be set using JavaScript by assigning a value to the document.cookie object. It used to be possible to set cookies using the HTML meta tag, but that is no longer supported by modern browsers. On the server side, in PHP, we can send HTTP response headers by calling the header function. However, manually constructing such raw setCookie headers can be error-prone. It is safer to use the setCookie function, which takes name, value, and an array of cookie attributes. This automatically handles the proper formatting of the header and will correctly encode the name and value if they contain special characters. Cookies that have been received from the client are available in the global cookie array. And raw request header values can be obtained using the getAllHeaders function. Let's look now at each cookie attribute in more detail. Attributes are quite important because if some attributes are omitted or used incorrectly, they can introduce security flaws that may allow an attacker to hijack the user session. First, let's look at the two cookie attributes related to lifetime. The first one, the expires attribute, can be used to indicate a timestamp for when the cookie expires, meaning when the browser should delete it. The second one, the max age attribute, can be used to specify the number of seconds until the cookie expires. If both expires and max age are set, then max age takes priority. If neither the expires nor max age attribute is set, then the cookie is called a session cookie and it will be deleted when the browser is closed. However, in practice, the cookie may not get deleted if the user has enabled the browser's session restore feature when restarting the browser. The cookie deletion is implemented by setting max age to 0 or by setting the expires timestamp in the past. So there is no dedicated delete cookie feature. The same setCookie method must be used to overwrite a cookie and force its expiration. Next, we have several security-related attributes, such as the HTTP-only attribute, which prevents JavaScript from accessing the cookie. This is an anti-cross-site scripting hardening feature, which we will cover in a separate lecture. The same-site attribute controls whether a cookie is included in cross-site requests. This is an anti-cross-site request forgery hardening feature, which we will also discuss in another lecture. Then there is the secure attribute, which indicates that the cookie must be sent only over HTTPS. And this is a very important attribute, because if not set, a network attacker could steal the cookie. And this is a good point for us to briefly step aside and talk about the difference between HTTP and HTTPS. So HTTP versus HTTPS. What is the difference? So by HTTP, we mean communication with a server that uses the HTTP URL scheme. The problem with this scheme is that our HTTP requests and responses are transmitted over the network in plain text. So anywhere along the network between our computer and the destination server, the confidentiality of our communication can be compromised. For example, if we are using public Wi-Fi like UT-Public to access a website over HTTP, then anyone nearby with basic equipment can see passwords and HTTP cookies that our browser sends to the website. To summarize, it is a terrible idea to use HTTP for anything important because it is so easy to eavesdrop on that communication. Today, all web communication should use the HTTPS URL scheme. The key difference is that here, our HTTP requests and responses are end-to-end encrypted between our browser and the server using the TLS protocol. To enable HTTPS communication on the server side, a public key certificate needs to be installed. But today, these certificates can be obtained for free, and setting it up usually takes just a few additional lines in the web server configuration. In this course, we will not go into how TLS works. If you're interested, you can take our Applied Cryptography course, where certificates and TLS are covered in detail. In this course, we'll just assume that the server administrator has already set up HTTPS for us. But alright, let's assume that our website is running over HTTPS. Are we safe now? Are we protected from the dangers of this unencrypted HTTP communication? Well, unfortunately, no. The problem is that today browsers still support HTTP communication. Therefore, our HTTPS website is still affected, meaning that we need to apply additional countermeasures to prevent plaintext HTTP attacks. Now, let's get back to the cookies and the secure attribute. As we mentioned earlier, the secure attribute indicates that the cookie must be sent only over HTTPS requests. If the secure attribute is not set, the cookie will be sent with both HTTP and HTTPS requests. Therefore, If a cookie is set without the secure attribute, a network attacker can trick the user into making an HTTP request and thereby steal the cookie. So here we assume a network attacker that controls the network traffic between our computer and the website. So if a website sets a cookie without the secure attribute, then an attacker can send us an HTTP link to the website, and after we click the link, our browser makes a plaintext HTTP request which includes the cookie, and the attacker can intercept it. The secure attribute helps to prevent this attack by telling the browser that the cookie should never be included in unencrypted HTTP requests. Also, an HTTP site cannot overwrite a cookie that has the secure attribute set. If an HTTP site tries to set such a cookie, the browser will reject it because there is an existing secure cookie with the same name. So, if our website sets the secure attribute for all our cookies, are we safe now? Surprisingly, not completely, because an HTTP site can set the cookie before the HTTPS site does, effectively injecting a cookie that the HTTPS site will accept. This works because the server does not know the attributes of a cookie it receives. The cookie header sent by the browser only contains the cookie value. Therefore, the server cannot distinguish whether it is a secure cookie set by itself or an insecure one injected by an attacker's HTTP site. Let's talk a bit how could an attacker benefit from injecting a cookie. Any ideas? The most straightforward attack is if an attacker injects their own session cookie, effectively logging the user into the attacker's account on the website. Now, you might ask, how is that a security issue? Obviously, it is bad if the attacker gets access to the user's account, but what is the risk if the user is logged into the attacker's account? Well, this depends on the specific website and timing of the attack. Imagine the user is performing some action on the website, maybe uploading or submitting sensitive data. If the user fails to notice that the user has been logged into someone else's account, the user might upload the data into the attacker's account, making it accessible to the attacker, right? Right. So this is a great example that shows how even seemingly minor capabilities of an attacker under the right conditions can lead to serious consequences. Cookie injection can also cause permanent denial of service attacks. For instance, if a web application does not handle unexpected cookie values properly and crashes with an error, then simply by injecting a malformed cookie could prevent the user from using the website until the user manually deletes the malformed cookie. This shows why web applications should not trust cookies blindly and should be able to handle even malformed cookies safely. Anyway, the good news is that recently browsers have introduced a workaround to help prevent this kind of cookie injection. So to prevent it, the cookie name must start with the prefix __ secure dash, as cookies with this prefix can only be set over HTTPS. This is what the set cookie header would look like. If an insecure HTTP site tries to set such a cookie, the browser will reject it. So setting the secure attribute and using the secure prefix is the best practice that every HTTPS website should follow. But even with this protection, we still want to go a step further. We want to prevent the browser from making any HTTP requests to our website. This is where we can apply the HTTP Strict Transport Security Policy, or HSTS. By setting HSTS for our website, we can prevent attacks where a browser is tricked into making an insecure HTTP request to our domain. So we should use it as a hardening technique against plaintext HTTP attacks. Note that it is not enough to configure a redirection from HTTP to HTTPS. Yes, it helps redirect users to the secure version of the site. However, if a browser connects over insecure HTTP, a cookie without the secure attribute may have already been transmitted in plaintext, just as we discussed earlier. But okay, even if our cookies have the secure attribute set, or even better, use the secure prefix, we still have a problem when a user makes the initial request to the insecure HTTP version of our site, because a network attacker can remove the redirect from HTTP responses so the user never ends up on the secure HTTPS website. This is known as a TLS SSL stripping attack. The idea is that a network attacker sets up a fake HTTP server for our domain, but this fake server does not redirect to HTTPS. And if the user does not notice that the browser is on the insecure version of the website, the user might submit a password unencrypted directly to the attacker. So this is where the strict transport security header can help us, as it enforces HTTPS on the browser side. After receiving this header, the browser remembers that this domain must always be accessed over HTTPS. So if the user later clicks on an HTTP link or even types in an HTTP URL, the browser will automatically convert it to HTTPS, preventing any insecure requests from being sent. The syntax of the header is as follows. Here we define in seconds how long the policy should be enforced. Here we can set the include subdomains flag to apply the policy to all subdomains. And the preload flag indicates that the domain should be included in the HSTS preload list. So after the browser receives this header over HTTPS, it will refuse to make any insecure HTTP requests to our domain and its subdomains in the future. By the way, Chromium has a convenient UI for managing HSTS and checking cached policies. Anyhow, as you may have noticed, the limitation here is that the policy is only in effect after the website is accessed over HTTPS for the first time. So there is still some attack window during which an attacker could execute these SSL stripping attacks on our users. The solution here is to specify the preload attribute in our header and submit our domain to hstspreload.org. This will inform browsers that they can ship this policy for our domain in the preload list that is shipped within all major browsers. So after a user installs or updates their browser, the policy will already be enforced for our domain before the user has even visited our website. To summarize, today this HSTS header should be returned by all websites that run over HTTPS. Hopefully, one day browsers will completely block insecure HTTP requests, and then we can get rid of this opt-in security mechanism. But until then, it is best practice to use this header. And by the way, both Firefox and Chromium browsers do support HTTPS only mode, but unfortunately, it is not yet enabled by default. At least the good thing is that today, when we type in a domain name in the address bar, browsers try to connect to HTTPS first and only fall back to insecure HTTP if a secure HTTPS connection cannot be established. This, however, will not help against an active network attacker who can block secure connections. That's why HSTS is still needed. Let's get back to the cookie attributes and talk about the domain and path attributes. First, the path attribute. The path attribute indicates the path that must be present in the requested URL for the cookie to be included in the request. In practice, it is safe to set path equals / and forget about it. If you set it to /, it matches all URLs and the cookie will be sent with every request to our server. If we don't set it explicitly, then the current path of the URL will be used by default, which might not be what we want, so it is safer to explicitly set it to ensure it applies to all paths. In theory, we could use the path attribute for security purposes, for example, to isolate cookies between applications hosted in different subdirectories of the same website. But as you will see in the future lectures, there are many ways for co-located applications to attack each other anyway, so we will not even try. Now, the domain attribute defines which host the cookie will be sent to. And this is a very security critical attribute, so please pay attention. When it comes to setting the domain attribute, we cannot just set here any domain we like. Only the current domain or a higher ordered domain can be set. Otherwise, the browser will simply ignore the cookie. For example, a.example.com can set a cookie for itself or for example.com, which is a higher order domain, but not for example2.com. What this means in practice is that cookies can be shared between subdomains of the same root domain, but not between unrelated domains. Now, what is important is that if the domain attribute is set, then the cookie will be sent to that domain and all its subdomains. This, however, creates a security risk because now example.com cookies can be stolen by a server at mail.example.com. So if we use the domain attribute, we need to be absolutely sure that none of our subdomains can be compromised, which in practice is too strong security assumption to make. However, if the domain attribute is absent, the cookie will be sent to the exact domain that set it. And that is the safe default that should be used. One more thing, other services running on the same server but different ports can also access cookies. So cookies are not isolated between services that are on different ports. Anyhow, as a rule, whenever we see domain attribute set on a cookie, this means that a potential security issue has been introduced. Very good, so we will not set the domain attribute in our cookies. Are we good and safe now? Unfortunately, no, because even though other domains cannot access our cookies, the root domain and all subdomains can still inject cookies. Why? Because any subdomain can set a cookie specifying the root domain. This means that something like mail.example.com could inject a cookie that will be sent to example.com. What attackers can gain from a cookie injection attack we already discussed. These attacks are known as cookie tossing, and the real challenge for an attacker here is making the server use the attacker's injected cookie instead of the legitimate one. So when the browser's cookie storage contains two cookies with the same name but different scopes, where this is the original cookie and this is the injected one from a subdomain, the browser will include both cookies in the HTTP request ordered by the time they were created. Now, the question becomes, how does the server handle this? This behavior isn't strictly defined, but for example, in PHP, the server will use the first cookie listed in the request header. So if an attacker wants to trick a PHP application, they will try to make sure their cookie appears first in the list. One trick to do that is to set a more specific path on the injected cookie. That way, the browser will send that cookie first and the attack should succeed. What is also worth noting is that a cookie can even be injected from an unencrypted HTTP site on a subdomain, but only if the cookie name does not start with the secure prefix and the user's browser does not already have a secure cookie with the same name. Anyhow, the good news are that there is a way to prevent cookie tossing attacks. To prevent such attacks, the name of the cookie must start with the host prefix. Since such cookies cannot have the domain attribute, they will be sent only to the same host that set them. Here's how the set cookie header should look. For it to work, the domain attribute must not be specified, the path attribute has to be set to /, and the secure attribute has to be present, and the set cookie header has to be received over a secure HTTPS connection. If an insecure HTTP site tries to set such a cookie or the domain attribute is specified in a cookie, the browser will simply reject it. So host prefix cookies actually include security properties of secure prefix cookies, meaning that host prefix cookies also cannot be overwritten by insecure HTTP responses. In other words, host prefix cookies are a stronger version of secure prefix cookies. The main takeaway here is that we should use host prefix cookie names for all our cookies, unless of course we have a specific reason to share cookies between subdomains. Now, As you can see, the cookie mechanism was originally built on the assumption that there is some level of trust between domains under the same root. And to some extent, that makes sense because if we control a root domain, we usually control all its subdomains too, at least at the DNS level. This is the assumption what drives the same-site policy, which is applied in various contexts across the web. But what is considered a same-site by browsers? A site is defined as a registrable domain name and all of its subdomains, or more precisely, it is the effective top-level domain plus one. Taking just the top-level domain plus one is not enough, because there are exceptions like the co.uk, where the effective top-level domain includes not just the top-level domain.uk, but also the second-level domain.co. And actually, there are many such exceptions, and they are maintained in something called the public suffix list, which is a list of registrable domain names that should not be treated as such. For example, GitHub.io is on this list because its subdomains are actually run by different users, and you want to prevent these subdomains from attacking each other using, say, cookie tossing attacks. So browsers rely on this list to decide what should count as a same site. Today, this same-site policy is used for several purposes. First, in the scoping of HTTP cookies. As you saw earlier, it is used to determine between which domains cookies can be shared. Then it is used in defining the process boundaries for the site isolation feature we discussed before, meaning that in modern browsers, websites that belong to the same site may share the same operating system process and memory space, which potentially allows them to attack each other if there is a vulnerability in the browser. And then it is used to enforce resource limits fairly. The idea here is to prevent a single entity from bypassing limits by just spinning up lots of subdomains. For example, Let's Encrypt applies rate limits to certificate issuance, and these limits apply to all subdomains of a single site. In practice, however, this can be easily bypassed because anyone can request to have their domain added to the public suffix list, which means that each subdomain would then be treated as its own site with its own separate resource limits. And finally, the same-site concept is used for attribution and reputation to figure out who is actually responsible for the content on a site. For instance, the safe browsing reputation applies to the entire site, not just to a single subdomain. Similarly, browsers might also group data by site, so it is easier for users to manage or delete resources all related to the same entity, and so on. Recently, with the rise of HTTPS, the same-site policy has started to apply isolation by scheme, meaning that HTTP and HTTPS versions of the same domain are no longer considered the same site. For example, the secure prefix and the secure attribute on cookies is an example of this kind of isolation. Anyhow, after the web was invented, it quickly became clear that the same-site policy was too weak to serve as the main security boundary of a website, because then it would be too easy for one compromised subdomain to attack all the others. Therefore, when JavaScript was introduced, it was decided that scripts in the browser should be isolated using the much stricter same origin policy, which will be the main topic for our next lecture. The last thing to mention in this lecture is that every modern browser today comes with a built-in interface, usually called developer tools, which can be used to debug anything related to a website. Here is a screenshot from Firefox developer tools, which can be opened by pressing F12 on a keyboard. Here we can see that the network tab is open. This tab shows all the network requests made by the browser for the current website. By clicking on a specific request, we can inspect both the HTTP request and response in detail. The Inspector tab here is also very useful as it lets us inspect and even modify the DOM of the page in real time. The Console tab can debug and run JavaScript code directly. And the Storage tab allows us to view things like local storage and cookies that are saved for the current website. Now, this was just a very quick overview, but I really recommend you spending some time getting familiar with what it can do, as it is going to be an extremely helpful tool for you throughout this course. And with that, we have reached the end of this lecture. Good luck with the homework assignment.